Hi everyone, my name is Nuralya binti Muhammad Bakri and today I will be presenting my project for MTES 3203 Mathematical Reasoning. Mathematics isn't just about numbers or formulas. It is a language of logic that helps us make smarter decisions in the real world. From designing building to conserving materials, mathematical reasoning allows us to find solutions that are both efficient and practical. In this presentation, I will explore one such real-world scenario, which is a community planning to build a closed water tank with a fixed capacity. The challenge is to determine which 3D shapes, a cylinder, a cube, or a triangular prism, use the least amount of material while holding the same volume. To solve this, I will be applying Polya's four-step problem-solving model together with algebraic and logical reasoning to analyze and compare each shape. By the end of this presentation, I hope to show how mathematical reasoning transforms complex problems into clear evidence-based conclusion and why it is an essential skill not just in math but in everyday decision-making. Let's begin. As shown on this slide, the main problem in this project involves a community planning to construct a closed water tank with a total capacity of 8,000 litres, which equals to 8 million cubic centimeters. The challenge is a straightforward in wording but deep in reasoning. Which shape, a right circular cylinder, a cuboid with a square base, or a right prism with an equilateral triangular base will require the least surface area to enclose the same fixed volume. At first glance, it might seem like a simple geometry exercise, but this question actually tests a higher level of mathematical reasoning. We're not just finding areas and volumes, we are exploring the relationship between volume and surface area and how changing one dimension affects the efficiency of the entire design. In real-world terms, the least surface area means using less construction material, which directly reduces cost and waste. So this problem mirrors how engineers and designers think when optimizing structures, finding the perfect balance between functionality, economy, and geometry. To solve this systematically, we will use Polya's four-step problem-solving model, moving from understanding and planning to calculation and final reflection. By doing so, we can reason through each step mathematically and logically, ensuring our final conclusion isn't just correct but justified. Before diving into the calculations, let's justify why algebraic reasoning is the most suitable method for this problem. When comparing three different 3D shapes, we need a way to represent the relationship between volume and surface area without relying on random measurements. That's where algebraic representation comes in. It allows us to express the problem symbolically using general variables instead of specific numbers. For any 3D subject, the relationship between surface area and volume can be represented by the proportional equation, which is S minimum equals to K times V to the power of 2/3. Here, K is a constant that depends on the shape's geometry. In other words, each shape has its own efficiency constant. By comparing these K values, we can determine which shape used the least material for the same volume. This algebraic approach highlights conceptual understanding rather than repetitive computation. Instead of guessing or substituting trial values, we reason through the structure of the formula itself, identifying patterns, simplifying variables, and making comparisons that apply universally no matter the scale. Later, in this presentation, we will calculate the K value for each shape, the cylinder, the cube, and the triangular prism, and then visualize the comparison through a bar chart. This method demonstrates how algebraic reasoning not only simplifies the process but also strengthens logical thinking, allowing us to draw precise and meaningful conclusions. Now, let's go through the calculation. According to Polya's four-step problem-solving model, we will start with understanding the problem. So, for the first step, understanding the problem, we want to find which shape, cylinder, cube, or triangular prism needs the least surface area to contain the same volume. To make a fair comparison, we express the surface area of each shape in terms of the same volume, V. for the second step, we need to devise a plan. Our plan is to write the formulas for surface area and volumes for each shape. Then we express one variable in terms of the other and simplify to express surface area as a function of volume. Using optimization, we find the minimum surface area and calculate the constant for each shape. The smallest constant value will indicate the most efficient shape. Now, let's begin with the cylinder. First, we define radius as r, height as h, volume as v equals to pi r square h, and surface area as s equals to 2 pi r square plus 2 pi r h, since the tank is closed on the top and the bottom. So, we already know from calculus that at the optimal point, h equals to 2r and r cubed equals to v over 2 pi. Now, substitute this into the surface area. S minimum equals to 2 pi r square plus 2 pi r h, which equals to 2 pi r square plus 2 pi r times 2r. So, S minimum equals to 6 pi r square. Now, we need to replace r using r cubed, which equals to v over 2 pi. So, r equals to v over 2 pi to the power of 1/3. Substitute back, S minimum equals to 6 pi times v over 2 pi to the power of 2/3. It equals to 6 pi times v to the power of 2/3 over 2 pi to the power of 2/3. It equals to 6 pi to the power of 1 minus 2/3 times 2 to the power of negative 2/3 times v to the power of 2/3. So, simplifying the constant, we will get S minimum equals to 3 times 2 pi to the power of 1/3 times v to the power of 2/3. So, the constant of cylinder equals to 3 times 2 pi to the power of 1/3, which is approximately 5.538. Now, let's calculate for the cube, which is a cuboid with all sides equal in length. For the cube, A equals to h, volume V equals to A cube, and A equals to V to the power of 1/3. Surface area S equals to 6A square, and then we need to substitute A. A equals to V to the power of 1/3. So, S minimum equals to 6 times V to the power of 1/3 square equals to 6 times V to the power of 2/3. So, from the formula, we can see that the constant for cube is 6. Next, let's move to the right prism with an equilateral triangular base. Let the length of each side of the triangle be t and the height of the prism be h. The area of an equilateral triangle is sec3 over 4 t square. So the volume is V equals to sec3 over 4 t square h, and the surface area is S equals to 2 times sec3 over 4 t square plus 3th. The first term is for the 2 triangular ends and the second term is for the 3 rectangular side. Now, express h in terms of V. h equals to 4V divided by sec3 t square. Substitute this into the surface area formula. S equals to sec3 over 2 t square plus 12V divided by sec3 t. Now, differentiate with respect to t set to 0. ds over dt equals to sec3 t minus 12v over sec3 t square equals to 0. Then we will get 3 cubed equals to 4v. Thus, t equals to 4v to the power of 1/3. Now, substitute t into h. Now, substitute t into S, we'll get S minimum equals to sec3 over 2 times 4 to the power of 2/3 plus 12 over sec3 times 4 to the power of 1/3 times V to the power of 2/3. Simplify numeric constant carefully, we'll get 4 to the power of 2/3 equals to 2 square to the power of 2/3. So it equals to 2 to the power of 4 over 3, 4 to the power of 1/3 equals to 2 to the power of 2/3. So S minimum equals to sec3 over 2 times 2 to the power of 4 over 3 plus 12 over sec3 times 2 to the power of 2/3 times v to the power of 2/3. So after simplification, this constants equals to 3 3 times 2 to the power of 1/3. So we will get that the constant for triangular prism is approximately 6.549. Now we come to step 4, look back, which means checking and reflecting on our results. We found that cylinder K equals to 5.538, cube equals to 6, and triangular prism equals to 6.549. Since the cylinder has the smallest K value, it means it's the most efficient shape, requiring the least material for the same volume. To visualize this more clearly, I represented the results in a bar chart, showing how much more surface area each shape needs compared to the cylinder. Here is the bar chart analysis. On the vertical axis, we have the constant K representing the efficiency factor. On the horizontal axis, we have the three shapes: cylinder, cube, and triangular prism. As you can see, the bar for the cylinder is the lowest, followed by the cube, and lastly the triangular prism. The cylinder used around 7.7% less surface area than the cube and 15% less than the triangular prism. This clearly shows that the cylinder is the most efficient design. It demonstrates how algebraic reasoning and graphical interpretation can be combined to make logical evidence-based conclusions. This diagram visually supports our conclusion. The height of each bar corresponds to the K value, showing the material efficiency of each shape. Through this process, we can see that mathematical reasoning allows us to make practical design decisions, not just through calculation, but by understanding relationship and patterns between variables. As we reach the end of this presentation, let's take a moment to reflect on the key takeaways. Through this task, we have seen how mathematical reasoning bridges theory and real-life situations. We begin with a practical question, which is determining which tank design used the least material and applied a structured logical process to solve it. By combining algebraic representation with Polya's 4-step problem-solving model, we approach the problem systematically, understanding it, planning, carrying out the steps, and finally reflecting on the result. The result showed that the cylinder is the most efficient shape as it used the least surface area for the same volume. This conclusion isn't just about shape. It highlights how mathematical reasoning helps us make smarter evidence-based decisions, whether in engineering, design, or everyday problem solving. Overall, this project demonstrates that mathematics is not only about numbers and formulas, but also about thinking critically, reasoning logically, and finding the most effective solutions. That's all from me. Thank you for your attention.